Hey there, in this video I want to talk about solving nonlinear equations. Let's start with an example equation. I'm going to go with x plus e to the negative 2x equals 1. And that's an equation that doesn't have an analytic solution. If you think about ways to solve an equation like that, you might think, well, let's plot what that looks like and see where do these two lines cross each other. And we can do things like that. But there's another approach we could take with a computer, which is to iterate on the solution. We're looking for something called a fixed point. So the key idea here is we want to rewrite our equation to be in the form x equals f of x. And then we can repeatedly run this through a loop, solving for a new value of x each time, hoping that it converges to a value that is the solution, or at least one of the solutions. This particular equation actually has two solutions to it, and we'll see how we can find each of them. So rewriting it in that form, well, there's a few ways to do that. That's actually an important part of this technique. There's choices to make, but what looks easiest to me would be to just move this x over here to the left-hand side, or leave it on the left-hand side. And on the right-hand side, I'd have 1 minus e to the negative 2x. And so what I should be able to do, and what we're going to try, is I'm going to pick a starting value for 1, basically guessing crudely what the solution is. You could do this by making a graph as a starting point. I'm just going to pick the value 1 because it's close enough to one of the solutions. And we're going to see what happens when I keep solving for x over and over again. So let's write some code that'll do that. F of x is going to be the function 1 minus x negative 2 times x. And I have to make sure I have numpy imported for this. I don't think I did that yet, so give me just a second. Numpy is np, and we've got to make graphs, right? So we'll do matplotlib.pyplot as plot. Okay, so now I can define that function, and let's iterate. So we're going to start with 1 as our starting value, so some kind of initial guess, and then we'll do a loop here. Let's just try doing this 10 times and print the result each time. Each time through, I'm going to redefine x over and over and over again, and then we'll print x each time. So the first value would be 1. That won't actually print, but then after 1 we get these next values. I didn't put any variable in my for loop. All right, so for I in range 10, print this out. So we started with 1, then we go to 0.864 and so on. So the first jump from 1 to 0.86, that was the biggest, and then our jumps are getting smaller and smaller, and it looks like as we get down here to the end that we are reaching a value 0.797, and it looks like we're converging there. Now let's check if we really do converge. And so basically we want to do more terms in our for loop. So we can copy that code. We want to make sure we reset x to the initial guess here. And let's do something a little bit different. Let's keep track of the values in a list. I don't want to print them all, but I want to keep them somewhere, and then you could do something like, say, plot them to see what they look like. So we're going to keep the values in a list. We'll do a much bigger for loop. Let's go 1,000 steps in here. And at each step, we want to stash our x. Let's start with a 1. So we'll do the stashing before we recalculate. Values.append the current value of x, and then we update x. And now instead of printing it, we just want to store them. And at some point, we should have some result that we consider good enough. Hopefully it doesn't take 1,000 steps. So let's make an if statement in here that will break out of the for loop. And we're going to check here for a relative difference. So we want to check x compared to the last thing we stored in x, basically the old value of x, because we all just stashed it in values. So if we look at the last element, that'll be the last thing in it. We compare the current value to the old value, and if that absolute value is less than, let's say, 10 to the minus 8, 1 part in 100 million, we call that good enough. We'd say, okay, converged. And in that case, let's print a message about that, and then we're going to jump out of our loop. And so our print statement can be something like x equals x after I iterations. Or maybe it's I plus 1 iterations, you know, close enough. Just to give us a crude idea of how often it runs, and we want to actually use the variable I. Now here's something else we can do for code like this. This will work, but suppose it didn't. It doesn't converge after 1,000 steps. This particular program would just do nothing. It would print nothing at all. And if we just put a generic, you know, print, let's see, I don't know, print failed. It would always print this, and that's not really what we want either. We want to write code that would print failed only if it doesn't converge. And so the cleanest way to do this in Python is to attach an else statement to our for loop. So for loops and while loops can have else statements, and the way this works is this only runs if the for loop finishes. And the hope here is that we will hit a break statement, and so it's not going to run. But if we don't hit that break statement, then the else statement will trigger and will print failed. All right, so let's see what happens. It took 18 iterations, and we converge. It looks like basically the same value we had before, you know, with just a few more decimal places. So, hey, 18 iterations to be good within one part in 100 million is not bad at all. So this is, you know, this can work pretty quickly. Let's look at how it converges. So let's plot the values. Not a very long list of values, so the graph won't be too cluttered. We'll plot them as dots. Let's just use it sort of as a visual sense of how does this thing converge. Okay, so we started up here at 1, and then we quickly just sort of almost exponentially converge onto our value. Okay, great. This is looking really good. So what about other solutions? I mentioned at the beginning that that particular equation has 2 solutions. And the way I knew that is I plotted it ahead of time. Let me show you that plot right now. So to make a graph, I want to do linspace of some value. So here, x is not a solution to the equation. It's just going to be x values. And we'll do our linspace from -1/2 to 2, and we'll do 100 of them. This is already some foresight. I already know that the solutions are going to be in that range. And then we're going to plot x compared to f of x, just using our function from above. And we're also going to plot a straight line. And the reason I want to plot x versus x here is that we're looking for when f of x is equal to x. That's when we have one of our solutions. And I'll just do that as a black solid line, so it shows up clearly on my graph. I'll draw a grid just to make it easier to eyeball the values, and then let's show it. Okay, so we have 2 solutions here. It looks like one of them is really close to 0, and in fact we can just mentally plug in 0 and see that that in fact has to be a solution. And the other one looks like it's 0.797, you know, or whatever we got before. That's our solution up here. Okay, so why did we hit this solution? Well, if you think about it, we started at 1, and you know, hopefully we are converging on something, and the first solution we would hit as we're converging would be this one. I could pick a value in between here, and then it's kind of, you know, it's not really random. There is some behavior to this, but you could imagine it could go either way. So why don't I pick a starting value over here to the left of 0, and then the only solution it should be able to hit would be the 0. Okay, let's just see what happens when I do that. So we already have some code that solves for us. Let's just copy that code. And the only thing I want to change is my starting guess. So let's start like right next to the solution. It looks like it's at about 0. So what if we start at -0.01, you know, and we'll let it run up to 1,000 steps, printing out success if we can find a solution that matches within one part in 100 million, otherwise printing failed if we can't find it. And it failed. So after 1,000 attempts, it wasn't able to get there. Not only that, but it's yelling at me here about overflows and invalid values encountered. Something has gone very wrong, even though we were super close to that other solution. So let's try to figure out what has gone wrong. Let's just plot all the values that we encountered and see what they're doing. And two things really stand out to me. First of all, the scale on this, 10 to the 16. So, it looks like we are around 0, compared to 10 to the 16 at least. And then all of a sudden, pow, we're down here. The other thing I noticed is, didn't we just run this for 1,000 iterations? Why aren't there 1,000 points on this graph? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points on the graph. So let's print our values, or at least the first few values. We'll go everything up to, say, 10 here in our values array. And this is where we started, great. And these are not approaching 0. They are actually getting farther and farther away from 0, exponentially so. You can see here we go from 18 to 10 to the 16 to infinity. And now you start plugging infinities into your equation and it just stays infinite all the way through. And that's what these error messages up here are all about. Okay, so this definitely hasn't converged. So let's see if we can figure out why the relaxation method fails sometimes. As a reminder, we've taken a nonlinear equation and written it in the form x equals f of x, and we're trying to figure out what the solution or solutions to x are. We're going to call the solutions x naught. Let's just look at just one solution. So x naught is just a single solution in here. And the way we solved this problem was we iterated. So we kept redefining x by making some guess and then calculating a new value of x over and over and over again. So during this process, let's say we are at iteration I. And during iteration I, we're calculating a new value of x, xi, based on an old value of x. We take our function and we plug in the old value. So that would be x sub I minus 1, so the previous value. Now let's see what happens if we Taylor expand the right-hand side to see why this sometimes blows up. And we're going to Taylor expand around the solution x naught. So the right-hand side becomes the function evaluated at the solution. And no, we don't know what that value is, but mathematically it would expand around that value, plus x at I minus 1 minus x naught. And just to clean that up a little bit, the minus sign is not in the subscript. That would be multiplied by the first derivative of f at the solution, and then so on for second derivative term, on and on and on. And if we did this infinitely, it would be exactly equal. Now also notice that f at x naught is by definition exactly the same thing as x naught, just based on the original equation we had. So now let's rearrange this, and we're going to cut off some of the last few terms. So we'll make it approximate. If I take xi and I move the x naught to the left-hand side, that would be equal to xi minus 1 minus x naught, all of that multiplying the first derivative of x naught, and so on with all the other terms. Let's call this first thing, so that would be this term right here. Let's call that delta x, and what that represents is the distance we are away from the solution. So at step I, I'm some distance away from the solution. Hopefully it's tiny, but sometimes it's not. And that is going to be approximately equal to the old distance away from the solution, multiplied by the first derivative at the location of the solution. And so the question is, does delta x shrink? Compared to its old value, is the new value getting smaller? And the answer is yeah, if and only if the absolute value of the derivative is less than 1. So if this derivative over here is less than 1, then we're going to get smaller every step. If the derivative here is greater than 1, then we grow every step, and that would be a case where we're not going to converge, where our solution explodes. Let's look at an example. In fact, it would be the one we just did. So again, we want to take our nonlinear equation and put it in the form x equals f of x. In this case, we had f of x being 1 minus e to the negative 2x. So we're iterating on x equals 1 minus e to the negative 2 previous value of x. And let's look at the derivatives here. So we can do this derivative analytically, and we get to the derivative is negative 2 e to the negative 2x. So if I take f prime and I plug in the first root we calculated, that was around 0.797. If I put that in, crunch the numbers, I get negative 0.797. 406. That value is less than 1. Hooray, that will converge. And it did converge. Now if we take our first derivative and we plug in 0, we get -2. -2 definitely has an absolute value greater than 1. Basically, we double the delta x every step. Oh no, that's no good. That will not converge. All right, so now how do we solve this problem? Well, remember where we started. The original equation we had at the very beginning was x plus e to the -2x equals 1. And we just had to put it in the form x equals f of x. And I mentioned there's a few ways to do that. I just went with what looked most obvious, which was moving the exponential to the right-hand side. But there's other ways we could write this. And if we write it a different way, we'll get a different derivative and we can get it to work out. So what we could do is we could write this in the form e to the -2x equals 1 minus x, and then take the natural log of both sides, solving for x. We'd end up with x is equal to -1/2 times the natural log 1 minus x. And so then that would be my new f of x. And just to check what would happen, if I calculate the derivative of that new f of x and plug in the point 0, I'm going to get a -1/2 times 1 on 1 minus x, plug in 0, is equal to -1/2. And -1/2 has an absolute value less than 1. So hooray! It looks like that's going to work. Let's try it. Coming back here to our starting equation, we found we needed to write it in a different way. I'm just going to copy it down here. And we want to write the equation in a different form. So we want it to look like x equals -1/2 times the natural log of 1 minus x. Make that a markdown cell so it runs. Okay. So we're going to define a new function. We'll call it f new to contrast it with f. That's what we called it before. And that's going to return -0.5 times the natural log, that's just called log, of 1 minus x. And then we'll do our code below to apply the relaxation method. So we can just copy what we had before. This is the code that failed. And the only thing we're going to change is instead of using the function f, we want to use our new function. And so we start with a guess that's close to where the solution is. And we're going to 1,000 times try to iterate, checking for convergence. And if we don't converge, we'll print a failure message. Otherwise, we will print a success message. And look at that. It didn't take too much, 19 iterations, and we ended up within 10 to the -8 of 0. So we could say, okay, 0 is a believable solution. And if you wanted more accuracy, you would just change this up here to whatever accuracy you need. And as you might expect, SciPy has a function that already does the relaxation method, so you don't really ever have to write out this block of code. The relaxation method is pretty simple. It's not too hard to code. But it's in there, and it's called fixed point. And it lives in the module called optimize. So from SciPy, import optimize. And then we can call it optimize.fixedPoint. And we can take a quick peek here at the documentation. It wants a function, it wants an initial guess. If your function takes more than one argument, then you can pass those in here, set your tolerance, maximum number of iterations. You can see how very similar this is to the code we just wrote. This has an advantage over the code we wrote. It uses something called over relaxation, which means that as it tries to take each step here during each iteration, it jumps bigger than the calculated step, and that kind of helps it find roots in cases that wouldn't have succeeded. So let's try it out. The original function we wrote was called f. That's the one that was just the simple x equals 1 minus e to the -2x, and our first initial guess was 1. So if we run that, we should get 0.797. Yep. We can also try it with our other solution. So we'll do f here with -0.01. Remember, this failed before using the function f. But in this case, it does work for us. The over relaxation saves the day as it happens. We could try this with f new. it works just as well. 0 and -0 being, basically the same value. We're within some kind of rounding error. Now let's try this first one with fnew just to see. So here it failed. So it's not foolproof. It's not always going to work. There is still, if the derivative is too big, you can still run into trouble. It's not quite as harsh as having to be less than 1, but you don't get away with every solution. Meaning here that you have to be careful with how you write your equation. So using the new version of the equation and trying near 1, it fails. Using either version of the equation around 0 worked. It's a little bit of an art, a little bit of trial and error here when you're trying to solve your equations. And that's just the nature of the beast here.